gentlemen, today's class recording has started. So, yesterday, we formally introduced the concept of a conserved quantity. So, when we say that something is conserved, what does that mean? It's saved. Or if we measure it, what would we see about it when we measure it? It doesn't change, right? That it would be the same at the beginning as it was at the end. And that's the idea of a conserved quantity. So, there we go. All right. The first conserved quantity that we formally introduced yesterday was conservation of energy. Meaning that if we look at the amount of energy in a problem, we'll find that the total amount of that energy will remain constant. Now, when it says total energy, right, that means all kinds of energy. That will become important a little bit later on today, right? But under certain circumstances, we can see the conservation of one specific kind of energy, that being mechanical energy. If we're going to see mechanical energy being conserved, what has to be true? Julie, go ahead. That's true. Under what conditions will we see that happen?
Closed system.
Not what I was looking for. Oh. That will happen for, we'll see, that will be for the total amount of energy. But if we want to look specifically at mechanical energy, we say that there can only be conservative forces acting on our object. So, yesterday we talked in more detail about conservative forces. There are two conservative forces, and what are those two kinds of conservative forces that we introduced yesterday?
Gravity
and
elastic.
Gravity and elasticy forces, like springs and trampolines and stuff like that.
No, well, trampoline is kind of
True. Yes. All right. And if there are only conservative forces acting on an object, we will see mechanical energy being conserved. And so we use this formula to represent that, right? MEI equals MEF, right? Where ME stands for mechanical energy and I stands for initial. So the initial mechanical energy has to equal the final mechanical energy, which is what conservation means. But remember that mechanical energy is actually a combination or a sum of three specific types of energy. So we can't just look at kinetic energy specific or kinetic energy by itself. We have to look at the sum total of all three of those together. Okay? Good there. All right. Did I show you the pendulum yesterday?
No.
I don't think I did. Okay. All right. So let me show you this simulation. Okay. So here is a simulation that shows a pendulum, and I have the ability to raise the pendulum to whatever height I want to, which I will do in a second. Okay, but I also have the ability over here on the right-hand side to show a graph that measures the amount of energy that pendulum has at certain points of its swing. Okay? So here's what I'm going to do. I'm going to take my pendulum and I'm going to raise it to 40 degrees above the y-axis. And if you look at the energy bars, which two went up? PE and total, right? Why did PE go up? Because it got higher, right? It went higher up than it originally was. So it now has gravitational potential energy, right? I think all of you know that if I let it go, what's going to happen?
kinetic energy.
Okay? kinetic energy is going to go up as potential energy goes down, all right? And I will put this on, well, first I'll do it on real time. Okay, so here we go. Let it go, and boom. And go. So, that's a little hard to see, so I'm going to slow it down. So we'll go quarter time. Okay? All right. So as we can see here, right, the green line's representing kinetic energy, the blue line representing potential energy, that as the pendulum gets higher and higher and higher, potential energy goes up and kinetic energy goes down. But as it gets lower and lower and lower, potential energy goes down and kinetic energy goes up. Just getting into it. All right. Question. Is mechanical energy conserved in this demonstration? Discuss with the person next to you. Is mechanical energy conserved in this demonstration? Go.
So it doesn't move somewhere.
Let it go.
You got it.
So when you're lifting up the weight, why is it
It kind of does while it's moving, but they're really, in this simulation, they're worried more about, like, technically the simulation hasn't started yet at that point in time. All right. Well, let's talk about that in just a second. That's where we're going next. Okay. All right. So, question: is mechanical energy conserved in this demonstration? Yes. There are two ways that you can tell me or explain to me that mechanical energy is conserved. What's one way? Rito, go ahead. It never goes over that 40-degree mark. That's important because if it went above the 40-degree mark, what would that mean about the amount of potential energy it would have? It would have more potential energy than it started with, and that can't happen. So that's one way. Actually, Rito, that wasn't one of the two ways that I was thinking of, but that's one way. So now there's three ways, okay? Alex, what's another way we can tell that mechanical energy is conserved?
the total energy stays the same?
That total energy bar graph remains the same height the whole time. It changes what percentage of it is green and blue, depending on how much kinetic we have and how much potential we have, but the total energy remains the same. Okay? There's a third way that we can tell that might not be as clear, but if you look at the screen, there might be one way you can tell that mechanical energy is conserved in this case.
As a gravity.
Okay, there is gravity, right, which is okay because gravity is a conservative force. But this simulation allows me to do something that I can't do in real life.
Can change the type of gravity.
That's how much gravity. That's changing the G value. Sorry, that's changing the G value. Okay, so here, let's do this. Okay, if I go to the moon, okay, planet X is like a mystery, so like you would have to like figure it out. Okay, but so if I go to the moon, Audrey, what do we know about gravity on the moon versus gravity here on Earth? It's less. So what should we see about the potential energy line if I change the gravity from moon gravity to Earth gravity? It should be less because potential energy depends on the effect of gravity, right? Ready? Here we go. Okay.
What? Oh my god, it's an uppercut. Wait, why is it coming back down? Because there's gravity.
Because there's still gravity, it's just less gravity. Right? Alright, so let's go back to Earth. Okay.
Oh, go to Jupiter.
Alright, so
gosh.
going to Jupiter. Alright, hold on.
Wait, why is
Wait, let's go for the...
Okay,
Wait, no, please, please.
going to Jupiter. Okay, well, let's go here. Alright, so there's potential energy, right? Okay. If I go to Jupiter, anybody, what do we know about gravity at Jupiter? Wow.
It's...
How big is Jupiter compared to Earth?
Big.
A lot bigger, right? How much gravity does it have?
A lot.
A lot more. All right. Ready? Here we go. Go.
Gonna stay.
Fall down. Planet X is like a mystery. Like you're supposed to like figure it out. All right. Yeah, so you could use it like as a quiz. All right. So then, let's do this. If we go 0G, right, that means that there is no gravity, or the effect of gravity is negligible, and this happens.
So is it just gonna keep going up forever?
Because what makes the pendulum keep coming back to the middle? Gravity. If there is no gravity,
I
okay?
want to see it break and then just float away. It's not gonna break.
Okay. Are we good with this so far?
Wait, why is it going all the way back?
Because the string is holding it in place, right? So it'll keep going around in a circle because of the string, and it won't go back and forth. So.
No, I haven't.
Yeah,
It's so bad.
all right.
Wait, do Planet X.
So,
Windows. To the walls. To the walls. I just watched that movie. The proposal?
okay.
We do real time?
But, now that we've messed around with that, if you want to do real time.
116?
What?
All right. So, again though, even on planet X, mechanical energy is still conserved, okay? We talked about that the total energy line remains the same height, and the fact that it keeps going to the same height each time, keeps hitting that blue line. But there's one other thing that we can do with this simulation that we can't do in real life. Over on the right-hand side, in the little green control window, I have certain things that I can control, and one of those things is friction. Where is friction currently set at? None. Meaning that the only thing affecting this pendulum is what? Gravity. Gravity is a conservative force, meaning that it conserves mechanical energy. But if we add friction, all right? So here.
This reminds me of a nightmare I had. Oh, is it slowly gonna stop? Go to lots.
Why doesn't friction work on planet X? Interesting.
It is working.
No, it wasn't working.
Interesting.
Let's go here. We'll go back to Earth, because Earth rules.
Can we do like one?
All right. Okay, so now I've added friction. What starts happening
There's my question.
then? So what starts showing up?
Thermal energy increases when there's friction.
Thermal energy increases when there's friction.
That's
Take
why
your
you rub
hands and rub them together, right?
I think I've done this every year in science.
Okay. However,
Conversion. No, conversion. Divergent. Transform.
It started out like so small.
right.
That's
It's
all.
gonna go back down.
I sure did twice.
What? All right, so I'll put it in real time to make this point a little faster. Okay, so, all right, now, question. Is energy conserved in this simulation?
Energy is
Yes. Energy is conserved. Is mechanical energy conserved? No. Right? The total energy line keeps remaining the same height, but a greater and greater percentage of it is occupied by which color? Red. So we're turning mechanical energy into thermal energy. Right? Rito, what do we see about the height that the pendulum is going each time? It's going less high each time because it's losing mechanical energy. It's losing potential energy. It's not going as high. Okay? Is friction a conservative force? No, there's only two kinds of conservative forces. They are gravity and elastic, right? Meaning that if I showed you this simulation, so here's a bouncing spring, okay? The one thing that I did on this demonstration to make it a little easier to understand, over here on the right-hand side, what did I do about gravity?
Equals 0.
It equals 0. So now the only kind of potential energy that is showing up is elastic potential energy, because we stretch the spring out. And then as the spring pulls the mass back towards the middle, or the starting point, which is the dotted line, kinetic energy increases. And then as we go past the middle, kinetic energy decreases because it slows down again. But in this case as well, what are we seeing about the total line? Staying the same, is mechanical energy conserved in this demonstration?
Yeah.
Yes. Because, again, where's my friction set up in the top right? At none. Right? If I increase the friction, what would we start seeing happening?
It would, wait, I was asking if the softening was
Okay. That just makes it like how stiff the spring is, so like how quickly does it bounce up and down, back and forth, okay? Or how long it stretches out, depending on what mass you hang on it. But that's a story for a different day.
Okay.
All right, we good with this?
Yeah.
Okay. Back of your outline. Because we did the friction on the pendulum, it's the same thing. All right. The friction that we added on the pendulum was our first introduction to the non-conservative force. Yes?
What?
We'll answer that question at the end. So the girl with the pendulum up the top?
Oh, she
Well,
hit me for
No, she doesn't get hit in the face.
Because
if it was conservative. If it was conservative. I thought it said if it wasn't conservative.
All right, so
Non-conservative.
non-conservative forces. When non-conservative forces do work on a system, mechanical energy is not conserved. Okay? This is Roman numeral number 3 on the back side. All right, we skipped that girl with the pendulum picture. Okay. Right? When non-conservative forces do work on a system, mechanical energy is not conserved. Okay? The amount of non-conservative work done on a system is equal to the change in mechanical energy. Don't worry, we'll explain. The amount of non-conservative work done on a system is equal to the change in mechanical energy. We summarize that idea with these two equations, which are actually the same equation, just written in a different way. So the first one says, the first one says, WNC equals triangle ME. All right? Let's decipher. Okay? First, what do you think W is going to stand for? Work. Subscript NC, considering what screen we are on, is going to stand for non-conservative. So the amount of non-conservative work is equal to triangle ME. We already know that the ME stands for mechanical energy, right? Have we seen the triangle before?
no.
Nobody? All right, the triangle is actually a Greek letter. Greek letter delta, okay? In math and science, we use the Greek letter delta to represent change, okay?
I knew that because,
Okay? So, well, Audrey, let me ask you this question then.
okay, I'm ready.
If we are going to figure out the change in something,
Yeah.
we need to know two things. If we want to know how much something changes, what do we need to know? Do you want somebody else to know? In general. Steve. How much did we start with, and how much did we end up with? If we're going to figure out the change in something, anything, we need to know how much we start with and how much we end up with. That idea is represented by the second equation, right, that shows up here, that says MEI plus WNC equals MEF. MEI, the initial amount of mechanical energy that we start with, plus however much work we do will equal how much energy we end up with. Going back to day 2 of this unit, what does work do? Work is defined as a transfer of energy. If we do work on something, the energy changes. By how much? Depends on how much work we do. Okay? If you still have it out, great. If you don't have it out, don't worry, I'll show it to you up here. If you have your quiz from yesterday, question number 8 on the back side says, work is done on a ball as it is thrown upwards. The ball is thrown upward hard enough to give it 100 joules of kinetic energy. How much work was done? And the answer is 100 joules. Why? Because that's how much energy we gave it. Right? Going back to this equation that we just looked at, right? If we start with no energy and we do 100 joules of work, how much energy are we going to end up with? 100 joules. Okay? Good there. The simulation that we just did was our first introduction to friction. Friction messes up our world quite a bit. Okay? So, friction generally, I can't say always, but friction generally does negative work on the system. So generally, it causes mechanical energy to decrease. Some people write it. Sometimes I don't. I mean, yeah, sometimes I do. I mean, I could just not give you outlines and make you copy it.
No. Stop complaining.
No.
So.
It's okay.
No, I don't want that because for you guys to write down everything that's up on the board just takes a long time. So.
And we already take forever.
All right, yeah, let's be serious about that one. All right. While mechanical energy is not conserved, total energy is always conserved. Just like on the pendulum simulation, right? The line or the bar graph that represented total energy always remained the same height. But what colors made up the total height changed. Friction, excuse me, friction turns mechanical energy into non-mechanical energy, usually heat, but not always. But the total amount of energy will remain the same. Non-mechanical energy.
Wait, why did you give us such a big line for this one?
Again.
Can I explain this?
Yes, right now.
Sorry, I was just, okay. I just read my mind.
Do that as well. All right, so do something for me. flip your outline back over to the front side. You have a description of conservative force. What does your outline say that conservative forces do? Kenny?
They convert a form of mechanical energy into a total amount of mechanical energy.
They don't change.
So, Valentina, go ahead.
They do not change the mechanical energy.
Conservative forces don't change the amount of mechanical energy, but what do conservative forces do?
They change the amount. Wait, no. They convert one form of mechanical energy.
Conservative forces convert one form of mechanical energy into another form of mechanical energy, like potential into kinetic, or kinetic into potential. Keeping the total the same, though. Friction, or non-conservative forces in general, will turn friction turns mechanical energy into non-mechanical energy. So conservative forces turn mechanical energy into other kinds of mechanical energy, but friction turns mechanical energy into non-mechanical energy, generally heat. Okay? So, here's this girl and this pendulum. It just so happens that this pendulum happens to be made out of a bowling ball. Okay? So, this is a pretty famous physics demonstration. Okay? So, this girl takes her pendulum bowling ball, okay, or her bowling ball pendulum, and she holds it right up to her face. Okay?
Like touching?
Touching. Like touching. I've done this demonstration. I've done this before. I don't have the equipment to do it here, but I've done it. So you can take my word for it that it works, right? So, right? So you touching, like so starting on your nose. She lets it go. It swings across, potential turns into kinetic, kinetic turns back into potential as it goes up the other side. Then potential turns back into kinetic as it comes back through the middle, and then kinetic turns back into potential, right, as it comes towards her face. But doesn't touch her nose. No. Never, right? Because, no.
Yeah.
If it was already starting touching your nose, it would only touch your nose again if, Rito, what was the only thing acting on it?
Oh, gravity.
If gravity was the only thing acting on it. Just like when it kept going up to that blue dot, or the blue line at the beginning of the pendulum demonstration. But with friction, this happens.
Oh, no.
Okay?
That's scary.
That graph, easy, that graph you have right in the middle of the bottom line on your outline, okay? Is mechanical energy conserved according to that graph? No. What's happening to the mechanical energy line? It's going down. And if we look at the potential energy graph, which is the blue dots, right? And you guys, it's just the dotted line. It starts off at a certain height. The next peak that it hits, is it as high as the original peak? Meaning it has less potential energy. The only way for it to have less potential energy is if it doesn't go as high. Right? Because remember, potential energy depends on height. Right? So it keeps going lower and lower and lower potential energy each time, but that means it goes lower and lower height each time. The graph in the bottom right of your outline on the back page has added these two lines. That's my question for you. What are they? So what does the dash, dot, dash, dot, dash, dot line represent?
I got this one. I got this one. Thermal energy.
The dash, dot represents thermal energy. Because what's happening to the amount of thermal energy as the pendulum swings more and more and more? It increases. It increases how much?
The same amount as the
the same amount that the mechanical energy goes down. What does the green line represent? Just energy in general, or total energy. Okay? Very similar to the bar graphs that we were looking at on the pendulum or the pendulum simulation. Okay? Good there? All right. Video. If you're watching the video, I know I'm talking to you guys, I'm really talking to people watching the recording. If you're watching the recording, you might not see the video because sometimes when I play streaming videos, it just shows up as a black square, so you might not get to see the video. But for those of you here in person, we'll watch this video.
Yeah, guys, if you're watching this video, I really sorry about it.
So look, all right, here, let's check our simulations, okay? One, the spring, right, with friction set at 0, just continues to go back and forth, right? Same height, same distance each time, okay? But our pendulum, right, still going, but a large percentage of the energy now made up of thermal energy, right? And that height has decreased greatly. Yes, sir? Yep. I left it running the rest of the time. What? Just another window that it was running the whole time. Good there? All right. Let's watch this here video. Okay. So.
There's you.
Yeah. So as I explained to some people before, the guy you're going to see in this video, his name is Paul Hewitt. He wrote a book called Conceptual Physics. It's a great read. You should read it sometime.
You wrote it.
What?
He's talking about himself right
We
now.
do the Newton.
Okay. So let's go here. Oh, we can do this one too. All right. And here's 1 minute and 7 seconds of pure entertainment.
Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not going to do much good if this 14-pound ball comes crashing through them, yeah? Watch this. I want to show you a nice physics demo. The ball that doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this. Take some energy to lift the ball, yep? Now it has energy of position. Call that potential energy. I let go, it turns into energy of motion, kinetic, back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push. You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher.
So out of the 1 minute and 7 second video, you guys were able to maintain focus for approximately 25 seconds. All right.
Wait, is that him older? The picture of you, is that him older? No, the picture of you.
You should watch the other one.
Wait, have testimony.
Watch the other one.
All right.
Watch the other one.
So,
Okay.
no, we have to finish.
Wait, watch that again.
All right. So,
Still recording?
yeah.
Oh.
All right. So, just to wrap this up here, okay? On the back of your outline, there is a picture of the girl, right, and her bowling ball pendulum. And it says, if mechanical energy was conserved when the pendulum swings from side to side, why would this be dangerous? It wouldn't go higher, it would go the same height that it started each time. So if you started touching your chin or touching your nose, guess where it's ending back up?
Right back in your face.
It's hitting your chin or your nose, right? In the now, this demonstration, as you just saw in the video, this demonstration only works if you take the bowling ball and you just drop it. If you push it, you're doing work. If you push it, you are doing work, right? And therefore, therefore you are going to change the energy, specifically making the energy get bigger. And if the energy gets bigger, guess where it ends up? Well, it ends up higher than it started, right? So if you don't move, that's your face. All right, good there. Tomorrow, hey, listen. Tomorrow we will do example problems in class where we put numbers to all of this, okay? That's the sheet I gave you today. I will record class tomorrow and post answers online, so if you're not going to be here tomorrow, you can see what we did in class.
Do I have to take my book home and already did homework?
If you already did that homework that was on the calendar last night, it's the same homework for tonight.
I was sort of confused about this.